Assalamu alaikum dear students. I welcome you to 37th lecture of probability and stochastic processes. We have been talking about Markov chains, which are a special collection of random variables. The special thing about this collection is that these random variables are well ordered. There is a first, there is a second, third, fourth. All these random variables realize their values one after the other in a predefined, well-ordered manner. And these random variables are identified with an index. So there is an x1, x2, x3. These 1, 2, 3 are indices, and they represent the sampling time at which these random variables realize their values. So at sampling time 1, first random variable realizes its value, even though the value is not predictable, but we can talk about probabilistic behavior of this random variable. Then the second random variable realizes its value, then third, and so on and so forth. This collection of random variables is not an independent collection. If the first random variable realizes a certain value, then it's going to affect the subsequent variables and the values that they are going to realize. But in Markov chains, if we are interested in the value of a certain random variable, say xn, this value is going to be affected by all the previous random variables. But if we know the value of immediately preceding random variable, that is xn minus 1, that is all we need to know to make a probabilistic model for the behavior of xn, the next random variable. So if we are trying to analyze the behavior of nth random variable, all we need is the value of n minus first random variable, because that random variable captures the whole history of the evolution of this collection of random variables, the way they realize their values. We talked about Markov chains, we talked about a few examples, example of a device which went out of order, then it was repaired either locally or in a specialized facility. Then we talked about a person trying to perform Hajj and going through unpredictable situations, and we talked about a few other examples as well. The examples we talked about in previous lectures had finite number of possible states. These states are usually labeled 0, 1, 2, 3, 4 or any other subset of integers. But the actual outcomes of these sequences of random variables need not be integers. They can be a finite or possibly countably infinite collection of any entities, any type of entities, any type of real life situations, any type of outcomes of any unpredictable sequence of random variables. If all possible outcomes of these random variables are finite or countably infinite, we assign them labels. We call them state 0, state 1, state 3, state 2, and all those other integer valued labels. And we identify these states with these labels, and Markov chain is usually shown with these labels: state 0, state 1, state 2, state 3. The collection of random variables that we deal with is usually countably infinite. We would like to see how this sequence of random variables evolves in an asymptotic manner, in long term. Even though in real life we may be interested only in a finite number of random variables, there is an unpredictable phenomena which realizes its values as time progresses, and we are only interested in these unpredictable values over a finite time for a finite number of realizations. But the model we follow, the model of Markov chains, usually is for countably infinite collection of random variables. For example, let's talk about an electronic device or a machine which we purchase and it works and sometimes it breaks and then it gets repaired. All these machines in real life have a finite lifetime. They become obsolete, they become totally old, and we have to discard them and buy a new one. So if we are going to model the behavior of such a machine, we may be interested in modeling it for a few hundred days or maybe a few thousand days. Similarly, when we are modeling the sequence of events that a person sees when he is trying to perform Hajj, we cannot talk about more than 100 years. Even that is long. If a person starts thinking about performing Hajj, in 5-6 years, he is going to do that if he has the financial resources. So the maximum number of observations, remember there were 3 in 1 year. So maximum number of observations that we practically want to deal with would be 20, 30, 40, 50. In this case also, we allow this collection of random variables to be countably infinite. We allow this sequence of events that a person sees to go on till infinity, even though practically we need to monitor only a finite number of years. When we are dealing with a possibly countably infinite collection of random variables, we can analyze this collection in many different ways. We can talk about probability distribution of any one random variable in this whole collection. We can talk about the probability distribution of 100th random variable, 30th random variable, 10th random variable, and in previous lectures we did find the probability distributions of these individual random variables. We use a different notation in case of Markov chains. We use pi. So pi is the probability distribution of a certain random variable in a big collection represented by Markov chains. So the subscript of this pi represents the sampling time. So if we are interested in finding the probability distribution of 7th random variable, we say pi 7, and in brackets we put the value for which we want to find the probability value. So if the random variables in the Markov chain can assume values in a state space of 0, 1, 2, there are only 3 states, and we want to find the probability distribution of 7th random variable, then we will be interested in finding the values of pi 7 subscript and in brackets 0 or 1 or 2. And these 3 numbers must add up to give you a 1. So total number of possible outcomes are either 0 or 1 or 2, and at 7th sampling interval, the total sum of probabilities assigned to these outcomes should be 1. And this holds true for other sampling instances also. In addition to talking about probabilities of individual random variables, we can talk about events and their probabilities which involve more than one random variable. For example, we can talk about joint probability distributions, where we say that probability of x7 being 0 and x10 being 2 would be this. We don't have to talk about 2 random variables which are next to each other, which are adjacent to each other. We can talk about probabilities of any number of collection of random variables. If we do so, then we are talking about joint probability distribution. We can talk about conditional probability distributions, and this conditioning could be in a case of conditioning outcome of one random variable conditioned on outcome of another random variable, or it could be probability of a collection of random variables, that is a joint probability conditioned on an other random variable or conditioned on a group of random variables. So when we are dealing with a large collection of random variables, we are dealing with many things. We can talk about many things to analyze the behavior of this big collection of random variables. In previous lectures, we only talked about states and their probability distribution at a certain sampling instance. In this way, we should not lose the sight of individual random variables and their probability distribution. So let's review quickly what we have covered so that we can go forward with a clear understanding that when we are dealing with Markov chains, we are dealing with a very large collection of random variables. So the first thing that I want to review is the probability distribution. As I said, they are denoted by pi. So when I say pi m with x in the brackets, I'm talking about probability of an event which involves only mth random variable. And the event is that mth random variable, the random variable which realizes its value at mth sampling instance, will be equal to 1. So event is that xm, capital Xm, the random variable with index m, takes a value of x. And probability of this event is represented by pi index m and in brackets x. Remember, x must belong to the state space. State space in the case of that device which fails is 0, 1, 2. In case of a person who performs Hajj, it varied from 4 states to 8 states to 10 states. So the value that we talk about must belong to state space, and probability of a certain event involving only one random variable with index m is represented by pi of m for value x. As I told you, there is a large collection of random variables that we are dealing with. When we are investigating the probability of mth random variable taking on a certain value x, it depends on previous probability distributions. What the previous random variables assumed their values. So pi m of x depends on the previous random variables and their distributions. So when we are dealing with a large collection of random variables and we are interested in finding probability of a certain random variable taking on a certain value, we have to find what was the history of previous random variables. And in case of Markov chain, all we need to know is what was the value of immediately preceding random variable. For this large collection of random variables in a Markov chain, we can talk about more complex events and their probabilities. For example, we can talk about joint probability, which involves 2 or more than 2 random variables picked from this collection of random variables forming this Markov chain. For example, we can talk about joint probability of many random variables, and they don't have to be consecutive. We can pick as many as we want. So we form a vector of random variables, a vector random variable, by picking random variable x at sampling time m plus n plus q, and this taking a certain value z, and other intermediate random variables are also included. Then we take random variable x at sampling instance m plus n taking a value of y, and some other random variables between m plus n and m, and lastly we take random variable at sampling instance m taking a certain value x. So we have a big collection of random variables with their indices, and them taking certain values, we want to find probability of this event. And if we want to find probability of all these combinations, we are finding joint probability distribution of a big vector of random variables picked from a huge collection of random variables in Markov chain. For this case of joint probability distributions, there is a special interesting case when we are dealing with joint probability of 2 random variables which are adjacent to each other. One is at sampling instance m, the other is at sampling instance m plus 1. If we want to find the joint probability distribution of 2 random variables, we can use the formula for conditional probability, which involves joint probability and the probability of conditioning element, we find that this joint probability of two neighboring random variables taking on values x and y is equal to probability of previous random variable taking on its value and the transition probability. This is a conditional probability, transitional probability, that probability of the next random variable taking value y given that previous random variable took a value x. This is transitional probability from x to y, that is xm, the previous random variable took a value of x, that is known. With this knowledge, what is the probability that the next random variable will take a certain value y. So joint probability of two consecutive random variables is very easy to find because this is what is usually used in Markov chains. The transition probability of two neighboring random variables taking on certain two values. The next logical thing would be to talk about joint probability of three consecutive random variables. So here we are dealing with random variables xm, xm plus 1 and xm plus 2. They take on values of x, y and z. When we are trying to find joint probability of these three neighboring random variables, we can manipulate this expression so that we transform this joint probability into conditional probabilities and unconditional probabilities. So this is equal to probability of the two random variables xm plus 1 xm multiplied by probability of the third random variable given that this event has occurred, that is xm plus 1 takes on value y, xm takes on value x. So conditioning event has two random variables xm plus 1 and xm, they take on values of y and x respectively. But since this is Markov chain and conditional probabilities are only affected by the value of preceding random variable, immediately previous random variable. For this conditioning event which involves xm plus 1 and xm, value of xm does not play any role. If we know the value of xm plus 1, that is y, that's all we need to know. Hence, this conditional probability can be replaced with its formula, that probability of xm plus 2 being equal to z condition on just immediately preceding random variable. And this is again a one-step transition probability from y to z. We can represent this with p y to z. And this joint probability of two consecutive neighboring random variable is again given by probability of the previous one multiplied by the transition probability from x to y. So if we have three consecutive random variables, their joint probability is multiplication of three things. First is unconditional probability of that random variable which has the smallest sampling time or smallest index, then multiplied by transition probability from that random variable to the next random variable, followed by multiplication with transition probability from the middle random variable to the random variable which has the largest sampling instance. You can certainly extend this idea, and if you are working with a Markov chain and you have n random variables, all neighboring, all adjacent to each other, then their joint probability is a sequence of entries in the multiplication where the first entry is the unconditional probability of random variable which has lowest index, and then transition probabilities from that lowest to the next, to the next, to the next, and to the next. So this regular expression is extensively used to find the joint probability of three or more than three consecutive random variables. So when you want to find the joint probability distribution of 2, 3 or more than 3 random variables in a Markov chain which are neighbors of each other. We are adjacent to each other. There is no gap. Then the formula is easy. All you need to do is find the unconditional probability of the one with lowest index and then a few transitional probabilities from that lowest index to the next, to the next, and to the next. We don't have to limit ourselves to cases where the random variables that we work with are all neighbors of each other. We can certainly work with collection of random variables with some gaps, and we can talk about joint probability of two or more than two random variables with gaps. We can talk about conditional probabilities of one random variable condition on a random variable which is far away from the one we are interested in. Let's see if we want to find the joint probability of only two random variables with a gap of one step. That is, we are interested in finding the probability of xm taking on a value x and xm plus 2. There is a gap. Nothing is being said about the random variable with index m plus 1. So we are interested in finding the joint probability of xm being equal to x and xm plus 2 being equal to z. Let's take this event and let's take its intersection with the whole sample space. And whole sample space is represented with this middle expression where I have said that this probability of certain event is equal to joint probability of this event and the whole sample space, which is that middle random variable x m plus 1 can take on any value. A, v is any value. When x m plus 1 can take on any value, it represents a certain event. It represents the whole sample space. So this probability is equal to this probability. And when xm plus 1 takes on its values which it can possibly take, the whole state space, then this probability of three random variables taking on certain values can be converted to a sum, that is partitioning of sample space. I already talked about this partitioning concept in previous lectures. So this is just a repetition of that. Now the partitioning is based on xm plus 1 taking on its possible values, all the possible values. So if xm plus 1 takes on a value y, and y can be 0, 1 or 2 in the case of that device which breaks down, or for other random variables it represents the whole state space. So when you have this random variable which involves the middle random variable taking on a certain value y, then you have to add such probabilities for all possible values of y belonging to state space. So this probability is equal to this, and this probability is summation of this probability of three events where the middle event takes on all possible values, and summation is for this middle random variable taking on its values. And when you simplify this, because we have just worked with joint probability of three consecutive random variables, you come up with this expression. So here probability of xm plus 2 being equal to z and xm being equal to x is summation over all possible values of y that the middle random variable take, and then summation of this expression. Please note that the last expression consists of three things: probability of the random variable with lowest index m, and then transition probabilities from x to y and y to z. In this expression, these three values are given and they get multiplied, and then we sum over all possible values of y. But out of these three expressions, only two are functions of y. You can certainly take this constant which does not depend on y outside this summation, and we are going to use this modified expression in later slides. So please remember that joint probability of two random variables with one gap, one step gap, is given by this expression where this constant term can be taken out. We are going to use this modified version of the formula in next slide. The next slide is about two-step transition probability. Here we are interested in this kind of conditional probability, that what is the probability of capital X m plus 2 taking a value z when we know it is given that xm, the one previous to previous random variable, takes on a certain value x. So if we are talking about conditional probability with one gap, we know the value of xm and we want to find what's the probability of xm plus 2, we can use the previous formula. First we are going to open this expression using the well-known formula of conditional probability, and this is equal to a division of joint probability of these two events divided by probability of this conditioning event. And this joint probability is the one we talked about in previous slide, and in that slide we said there is a constant term which can be taken out, and that constant term was exactly this. So that cancels out and we are left with just this summation, and this summation says that two-step conditional probability of xm being x and then xm plus 2 being z is summation over y, where y represents all possible values of state space that the intermediate point y can assume, and then multiplications of transition probabilities. These are one-step transition probabilities from x to y and then y to z. This expression should make sense because this conditional probability, knowing that we are here and we want to go to this random variable in two steps, involves all possible steps from x to intermediate point y and then from y to next point where the xm plus 2 takes on a value of z. If we look carefully, then this summation is inner product of a row and a column of the probability transition matrix, the one-step transition probability matrix, where this y takes on all possible values and we have this row multiplied by this column. So this is actually the element at location x row and z column for that matrix that we obtain by multiplying the one-step transition probability matrix with itself. So if we want to find two-step transition probabilities going from x to z, then that value of transition probability is found in a matrix that we obtain by multiplying one-step transition probability matrix with itself and then looking at row x and column valued z. So this summation is representing one element in that matrix at row x and column z, and that is exactly we are interested in. And if we have this collection of all possible two-step transition probabilities, we have a two-step transition probability matrix. We can represent it with simply P2, which is showing that we are working with two-step transition probability without this. When we are using this, then we are looking at x comma z element of that matrix, or we are looking at two-step transition from x to z. So there are many interpretations, and this should make sense, and you should work on these two-step transition probability matrices for simple Markov chains, like the Markov chain of a device that fails and gets repaired locally or in a centralized special facility. We can work with transition probability matrices with more than two steps. We can talk about three-step transition probabilities and the matrix associated with that, or four-step transition probabilities and its own four-step transition probability matrix. But as we saw, that the 3-step transition probability matrix is going to be multiplications of 1-step transition probability matrix with itself 3 times, or third power of 1-step transition probability matrix. Similarly, 4-step transition probability matrix is going to be 4th power of 1-step transition probability matrix. So by taking higher and higher power of these matrices, which are 1-step transition probability matrix, we can find n step. N is any big step, 5, 6, 10, 20. We have n step transition probability matrix on our hand. But the question is, how do you find higher powers of matrices? If you have a matrix, say 3 by 3, you can multiply it with itself. That is not very long computation, and when you have the result, you can multiply it with p again to get the third power, and if you want the 4th power, you can multiply the second transition probability matrix, that is 2-step transition probability matrix, with itself, so you get 4 power. So there are many ways you can do that, and for large matrices it really helps if you have a MATLAB or other matrix manipulation software package. In MATLAB you have a large matrix and it is so easy to take its higher power. In previous lectures, when I took higher powers of such transition probability matrices to find the probability distributions of random variables at index 30, 100, 150, I use MATLAB to find 1/50th power of 1-step transition probability matrix. You should also use MATLAB so that it is easy for you to move quickly to the result, get the result, and visualize the idea behind the result instead of getting bogged down with actual computations of higher powers of these 1-step transition probability matrices. So suppose you have MATLAB, you have higher powers of 1-step transition probability matrix, which gives you n-step transition probability matrix. So if you have n-step transition probability matrix, you can talk about joint probability of a collection of random variables with gaps using these n-step transition probability matrices. An example is being shown on your screen, where we are interested in finding the joint probability of 2 random variables xm and xm plus n. There is a gap of n-1 steps between these 2 random variables. But it should not be a problem, because this joint probability can be broken into unconditional probability of the random variable with lower index, and then conditional probability of having this lower index random variable a value x and going from that value to higher index random variable taking the other value y. And this is nothing but n-step transition probability, which is shown here. So if you have information about n-step transition probabilities, you can find the joint probability of random variables which necessarily are not neighbors or adjacent to each other. So by working with unconditional probabilities and conditional probabilities, which are also called transitional probabilities or transition probabilities, you can find probabilities of interesting events involving neighboring random variables or collection of random variables with some gaps in between. When you have tools to find joint probabilities and conditional probabilities of arbitrary collection of random variables adjacent or non-adjacent, you can work with many things. And this is the kind of analysis we use to find meaning behind different questions asked about Markov chains. One last thing that I would like to review is where this n-step transition probability matrix is used is when we are interested in finding the probability distribution of a certain random variable. So if you are given probability distribution of a certain random variable and you have your n-step transition probability values in the form of a matrix, you can use that matrix to find probability distribution of a random variable with index n plus the index of the random variable whose probability you know. Usually you start with probability distribution of 0th random variable, capital X index 0, the random variable from where the Markov chain starts its evolution, from where you start your sampling instances, you start your observation. So you start with probability distribution of capital X 0. If you have that and you have one step transition probability matrix, you can go to one step higher value of random variable, that is capital X1, and find its probability distribution. You can keep on going higher, but if you have n step transition probability matrix, you can use that and initial probability distribution to find the probability distribution of nth random variable. This is all summarized in this visual that you see on your screen, which says that m plus 1th random variable, capital X m plus 1, has a probability distribution which is probability of this random variable taking on a certain value. And you take its intersection with sample space, that is the previous value, and you continue this analysis and you end up with this expression which shows that the m plus 1 probability distribution can be obtained by taking the xm, the m level, the m sampling instance probability distribution, and then multiplying it with appropriate values of one step transition probabilities. And this is summarized as matrix multiplication, where pi m plus 1 represents a row vector of probability distribution of random variable capital X m plus 1, and this is equal to the row vector pi m multiplied by p, where p is one step transition probability matrix. And similarly, if you want to find the probability distribution of random variable with index m plus n, starting with probability distribution of random variable with index m, you have to use n step transition probability matrix, which is simply equal to nth power of one step transition probability matrix. So all these ideas have been talked about previously, and we have used these ideas to find probability distributions at sampling instance 30, 50, 100, 150, etc. So when you are working with Markov chains and you have your transition probability matrices, one step and n step, and you have your initial distributions, then you can find probability distributions of other random variables. You can find joint probabilities of more than one random variable, and you can ask many other questions about the behavior of this Markov chain. And by behavior of this Markov chain, I mean the pattern of values that the random variables in Markov chain assume. The pattern would be that first random variable takes on a certain value, second random variable takes on a certain value, third random variable takes on its own value. So this pattern of these well-ordered random variables taking on their respective values, that is what we observe. Based on that observation, we categorize Markov chains and we categorize individual states of the Markov chains. If there is a Markov chain and these random variables, as they evolve, as they take on their values, the values that they take can be a certain value in the state space again and again. That is, the random variables as they evolve visit that state, take on that value again and again. If that's the case, then that state is a recurrent state. And if those random variables take on a certain value a few times and then they evolve in such a way that they never take on that value, then that value, that state is a transient state. We talked about transient states and recurrent states in previous lecture, and in coming lectures we are going to rigorously analyze the behavior of Markov chains in terms of its behavior regarding being transient or being recurrent states. Let's look at another interesting aspect of Markov chains, and that is reachability. The proper definition of reachability is that a state y is reachable from state x if during the evolution random variable takes on value x, and then later random variables eventually somewhere down the road take on value y. So after taking on value x, it is guaranteed that the value y will also be taken by a subsequent random variable. If that's the case, then the state y is reachable from x. That's the proper definition of reachability. But let's talk about a much simpler version. Let's call it one-step reachability. One-step reachability means that during the evolution of Markov chain, while the random variables in Markov chain take on their respective values, state y is reachable from state x in one step if previous random variable takes on value x and next random variable takes on a value y. Let's look at a particular example. The example is the old example of a machine which breaks down and gets repaired in two facilities. This is the state transition diagram, and you can see that from state 0 we can reach state 2 in one step. So state 2 is reachable from state 0 in one step. Similarly, state 2 is reachable from state 1. But state 1 is not reachable from state 0 in one step because there is no jump from state 0 to 1. That means if the specialized repair facility cannot repair it in one day, they are not going to send the machine back to the local facility. So there is no way you can move from state 0 to state 1 in one jump. If you want to move, you have to go to this state where machine is working again, and unfortunately it breaks down the next day or a few days later, and then you reach 1. So state 1 is not reachable from state 0 in one step, but state 2 is reachable from 0. You can have a look at this diagram and see which states are reachable from other states in one step. And if you look at its state transition probability matrix, that is transition probability matrix with one step, you can see that certain values are 0. These 0 values represents those transitions that are not possible in one step. For example, from state 0, you cannot go to state 1 in one step. From state 1, you cannot go to state 1 itself in one step. That is, if you have reached state 1, the next morning you are either going back to state 2, which is that machine gets repaired, and if it cannot get repaired in one day, it moves to the other facility. And here, from state 2, you cannot move back to state 0. That is, if the machine is working and it breaks down, you cannot directly send it to the specialized repair facility. So these 3 zeros represents those transitions which are not possible in one step, and there are the cases where one step reachability is not applicable. Let's look at two-step transition probability matrix. Here in two-step transition probability matrix, you see that all values are non-zero, which means all states are reachable from all other states in just one step. So once you have this transition probability matrix with step size 2, subsequent transition probability matrix are also going to have all these entries which are going to be non-zero. Think about that. When this state transition probability matrix has all values non-zero and you multiply it with this one-step transition probability matrix, you are going to have a matrix with non-zero entries everywhere. So if you keep on going and you take an asymptotic value, that is P infinity, the long time transition probability matrix, you are going to have this value. This has converged. And when this has converged, then it means you can start with any probability distribution at sampling time 0, and in the long run you are going to have a probability distribution where machine will be in state 0 with a possibility of 4.3%, it will be in state 1 with a possibility of 8.7%, and it will be in a working condition with a possibility of 87%. So when you start with P, one-step transition probability matrix, you see some zeros, you take its powers, power 2, you get a matrix with all non-zero entries, then you move to P infinity and you converge to this matrix, which gives you a unique long-term asymptotic stationary probability distribution of 0.043, 0.087 and 0.87. Let's look at other examples and see if we can have a clue about the behavior of Markov chain from its state transition probability matrices. Let's take another example, a hypothetical example of a Markov chain which has only 4 states, 0, 1, 2, 3. This is called a random walk with reflection. The walk is from state 0 to 1, 1 to 2, 2 to 3, and once you reach this state 3, you reflect back to state 2 with probability 1. And then from state 2, you either go to state 3 or state 1. From state 1, you either go to state 2 or state 0. And if you reach state 0, you reflect and go back to state 1 with probability 1. So this Markov chain is called a random walk with reflection, and associated transition probabilities are also shown. Let's look at its one-step transition probability matrix. For this chain, this is the one-step transition probability matrix, and you can see that there are many zeros in this, which show that these states are not reachable in one step. You can have a zero and interpret its meaning by looking at its location. For this zero, it means you cannot move from state 0 to state 3 in one step. Of course, you cannot, there is no direct link. But if you take higher power, that is 2-step transition probability matrix or 3-step transition probability matrix, you might see different things. Let's have a look at these matrices. The 2-step transition probability matrix is shown here, which has different values, but still it has many zeros. Similarly, 3-step transition probability matrix, which is just third power of this 1-step transition probability matrix, it shows that the values of non-zero transition probabilities has changed, but still there are many zeros. And if you take its asymptotic value, its large power of 1-step transition probability value, you will notice something. You will see that in 4-step transition probability matrix, the situation is different only in terms of the values of 4-step transition probabilities. Similarly, for 5-step transition probabilities, the values are different, but still there are many zeros. And if you take the asymptotic behavior, then you see that if you take an even power, 2k, k is an integer, if you take an even power of 1-step transition probability matrix, you get a matrix like this asymptotically. And if you take the next power, that is, if you multiply this matrix with 1-step transition probability matrix, you get this. And if you multiply this, P 2k plus 1, again with 1-step transition probability matrix, you are going to get back this. So asymptotically, you are going to switch between this and this matrix depending upon the power. If the power is even, you will get this. If the power is odd, you are going to get this. So there are always going to be zero values transition probabilities for n-step transition probability matrix. And there is a way to interpret it. Let's look at this diagonal. This diagonal represents probability of coming back to state 1 in 2k steps, or 2k plus 2, or 2k plus 4 steps. And here, the same diagonal which has all zeros shows that probability of coming back to original starting point in odd number of steps is going to be 0. If you look carefully at that state diagram, you will realize that indeed that is the case. You do need even number of transitions to be able to get back to the starting state. And if you have odd number of transitions, there is no way that you can come back to the starting state. The last example of Markov chain that we are going to analyze for behavior of n-step transition probability matrix is the example of a person who tries to perform Hajj, goes through different states, and is allowed to reapply for another Hajj when he has already performed it. And if he chooses not to, then he can move in this loop. There are a total of 8 states, and its one-step transition probability matrix is an 8 by 8 matrix. You can take on its higher values, and you will see certainly for one-step transition probability matrix there will be many zeros. For example, you cannot move from state 0 to state 7 directly in one step. So there will be 0 in one-step transition probability matrix. But if you take higher powers, then you will get a pattern. And if you have guessed it correctly, you will get a pattern in such a way that if the power of one-step transition probability matrix is divisible by 3, you will get an asymptotic stable matrix. And if you take a power which is not divisible by 3 but gives a remainder 1, you will get another matrix. And if you take a power which is not divisible by 3 and gives a remainder of 2, you will still get another matrix. And if you take another higher power, you will get the matrix which you get for the powers which are divisible by 3. So there will be 3 matrices that get switched from 1 to 2nd to 3rd if you take higher powers of this transition probability matrix for this Markov chain. Let's summarize what we have covered today. We started with joint probabilities and conditional probabilities of different collections of random variables in a Markov chain. Then we talked about one-step transition probabilities and n-step, multiple-step transition probabilities and their associated matrices. And we are looking at a particular behavior of asymptotic higher powers of one-step transition probability matrix. We looked at 3 examples. And in first example, when we took the power 2 or higher power of one-step transition probability matrix, we got a matrix which had all entries which were non-zero. And then we saw that this particular Markov chain has an asymptotic, stationary, non-variant, steady probability distribution. In the second example, we took a random walk on 4 states with 100% reflection. And in that case, we saw that as we take on higher and higher powers of one-step transition probability matrix, we never get a higher transition probability matrix with all entries being non-zero. And asymptotically, we got 2 matrices, and as you continue taking higher and higher powers, you switch between 2 matrices. And for this particular case, this Markov chain is not going to have a unique, stationary, asymptotic probability distribution. And the third example, we already worked on this example previous lectures. In that example, we modeled the behavior of a person trying to perform Hajj. For this case, the one-step transition probability matrix was an 8 by 8, and I did not show you the actual matrix or its higher powers, but you can certainly use MATLAB to solve this. But the end result was, based on our previous working, that asymptotically higher and higher powers of this one-step transition probability matrix is going to give you 3 matrices, and higher and higher powers are going to circulate between these 3 matrices. It's going to be first matrix, second matrix, third matrix, again first, second and third. And this case also does not have a stationary, unique probability distribution. Actually, it has 3, and the previous example of random walk has 2. In next lecture, we are going to mathematically analyze why is it that if a matrix which has all entries non-zero and it has a unique single stationary higher power n step or infinite step stationary fixed transition probability matrix, then it's going to have a unique stationary distribution. And if it is going to switch between 2 matrices, then there will be 2 probability distributions. And if it switches between 3 matrices, it's going to have 3 stationary distributions that will get switched one after the other. Why is it so? We are going to analyze in next lecture, and we're going to do that with concepts of eigenvalues and eigenvectors. So before next lecture, I urge you to revise your knowledge of eigenvalues and eigenvectors. Till next lecture, I wish you the best. Thank you. Khuda Hafiz.